Alright guys, welcome back. So we're at lesson 2.10. This one's on force diagrams. Another way you could have heard their name is free body diagrams. I typically just call them force diagrams. That way kind of know what I'm referring to because they're really all about forces. So to start this out, we're going to look at a little image here. This is a block and it's sitting on an incline ramp. I just want you to kind of picture this yourself. If I have a block sitting on an incline ramp, what you'll know is that um, as long as this ramp has some sort of friction associated with it, as the ramp is, moved from a flat plane to a more inclined plane, it tends to start to glide down the inclined plane, right? The steeper the ramp or the inclined plane, the more likely the book is going to slide down the plane. Well, why is that? What forces are acting on the book? And why does the book eventually slide? Why doesn't it slide right from the beginning? What is the angle of the plane have to do with that? Well, it has to do with the forces acting on the plane. We're going to get into that. So, we're going to talk a little bit about inertia and also Newton's first law of motion. This law of motion is also kind of referred to as the law of inertia. So the law says that an object will not change its motion, an object at rest or an object in motion will not change unless it's acted on by an unbalanced force. Let me say that one more time. An object will stay at rest or remain in constant motion unless acted on by an unbalanced force. There it is, word for word, sorry. Okay, so if it's at rest, it's going to stay at rest. If it's in motion, it's going to continue to stay in that exact motion, constant linear motion. And I've talked about this a little bit before. So why is that? Well, this all comes down to inertia. Inertia is a property of matter like acidity, color, um, pH, whatever. There's lots of different properties of matter. Um, uh, melting point, whatever. So it's a property of matter that states that an object is going to continue to its existing state of rest or uniform motion unless it acted on by a universal or external force. Okay, it's these things like to stay where they're at, stay what they're doing, resistance to change, anything that has matter. And the more matter you have, the greater mass you have, the more resistance to change you are. You'll know this if you go to push a 300 kilogram boulder or a 30 kilogram boulder, right? Which one's going to be harder to move from its position? The larger one, right? And that's because it has more inertia, more resistance just to stay put. Also, if that 300 kilogram boulder was moving in constant motion and you had to slow that down versus a 30 kilogram boulder, which one are you going to have more luck slowing down? The 30 kilogram boulder, right? This will come towards momentum, but basically, the greater the mass, the greater the inertia, which means it's going to take more force to change that object's motion. Okay, so if we look into this, we're going to have to represent these different forces in different directions with some type of diagram. And what that's going to come down to is drawing force diagrams or free body diagrams. They use these in middle school, they use these in high school, and they use these in physics in college. Use it all around because it helps you understand the different vectors associated with the forces and their magnitudes. So ultimately, you're drawing a box to represent the object you're investigating. Whatever object it is, I don't care what it would look like illustrated, detail for detail. You're just drawing a box. Okay, so you draw a box and then you identify its center of mass. Where is the point within the whole mass where it's considered to be concentrated? Like if I were to, where would the balance point be, basically? So you would take that and you would mark that as your center, okay? And then you're going to identify the different forces acting on the object. And what's their direction? What's the magnitude of them? Which ones are larger than others? Okay, the larger magnitude objects should have longer arrows. We talked about this when we talked about scalar and vector quantities in 2.2, right? So, and then ultimately, what direction are they pointing? Okay, and then you're going to add all the forces up according to their respective vector, according to their direction, because ones in opposite directions actually cancel out. We're going to talk about that a little later. And then ultimately, you will decide whether the object is balanced or unbalanced. A couple rules to drawing free body or force diagrams. Always start the arrows in the center mass. Always start them there. Okay? And never draw the arrows facing into the object. It's like a pet peeve of mine as a science teacher. Some physics professors and teachers allow this, and they think this is fine. I prefer to have all arrows facing outward. So if it's applied force from the left and it's being pushed to the right, so I'm pushing on a box from one side and it's moving to the other, I'm pushing, I still want the arrow on the other side facing outward. Okay, so make sure that the arrows are the correct size and length in order to correctly represent the magnitude. Okay, the longer the arrow, the stronger the force. 4, always label the forces appropriately. I don't just want an arrow. If you give me just an arrow, I don't know what force you understand that is acting on the object. I won't be able to decide how to further investigate the object. 5, gravity is always straight down, and just like we talked about in 2.9, normal forces are perpendicular to the surface that object is on. Notice the ramp, okay? If you notice the ramp in the beginning, where's normal force pointing? Upward, perpendicular to the ramp. Gravity's pointing down, okay? That's the way it always has to be. So, how do you find out if a force is balanced or unbalanced? Great question. Glad you asked. So, what you're going to do is you're going to take the, I'm trying to move this just a hair just so I can get in there. All right. So you see this 100. So you're going to draw your diagram. You're going to add all the existing forces respected to their vectors. So in this case, I have 100 newtons of normal force pointing up. I have 100 newtons of force of gravity pulling down. Those two will cancel each other out, right? Those two balance each other out. That's the reason why normal force is there. It's just strictly to balance the object resting on a surface. Okay, it's always equivalent to the force of gravity of an object resting on a surface. So, in this case, those two cancel each other out. What's the only other leftover force? Well, we need to sum those directions too. Nothing on the left, 12 newtons of applied force on the right. In this case, what's left after all of this has been summed is 12 newtons on the right. 12 newtons on the right. And this makes that object unbalanced because there's not 12 on the left to balance that out. So consider it like a teeter-totter, okay? Like a four-way teeter-totter. The up and down are balanced. However, the right has nothing to balance itself out with on the left, okay? So in this case, anything but 0, if there's any force left over after you've drawn the diagram where it cannot be balanced, if there's any sum that is greater than 0, the object is unbalanced, okay? But if the sum of the forces is 0, the object is balanced. And this is how we decide how the object's motion is going to change. But I'm going to go ahead and save that for the next video. So at this point, you should just understand sum of forces, whether an object is balanced or unbalanced, and how to draw force diagrams. Review this, make sure you follow the rules, and you'll have great success. And we'll talk about Newton's second or Newton's first law in the next video. All right, guys, take it easy.